This is my Project 3.4.1 SAR ADC clock and overview. Here we can see the NOT gate IC with the 510 ohm resistor hooked up to the input between the input gate and the output gate, and then we see the capacitors in between the output of one of the gates and the input of the other. Here we can see the oscilloscope reading of the inverting oscillator with a period of 103 picoseconds and a frequency a little under the 10 kilohertz. This is an overview schematic of the SAR ADC in total. It is composed of 11 ICs and has two power sources, being a 5-volt power supply for the ICs, and then a positive and negative 9 rails power supply for the op amp to match the AC signals that are coming in. Now let's zoom in on this clock circuit. Here we can see a close-up of the clock portion of the SAR-ADC. For starters, let's say that at the floating voltage, this logic buffer is set to 0 to begin with. Now, when this happens, this is going to set this logic buffer to 1, which pushes electrons through to this capacitor, which has them output electrons from this capacitor, as the way capacitors function. What this means is that this plate is continuously charging up and this plate is outputting, meaning this value is a 1, this value is a 1, and this value is a 0. This means that current is going to begin flowing to the ground source over here, and also through this capacitor, through this plate, trying to get to this ground source over here. This is going to continue until this plate and this plate are completely charged. And at this point, no more current will be let through this capacitor. And at this point, when this happens, when there is no more current that is able to be achieved through, the 1 is going to flow through this resistor and then set this value to be a high, setting this to a 0, and then the capacitor begins to discharge through this ground source, making this side high and reversing the entire circuit. This will continue over and over again, creating an inverting oscillator. Here we can see that exact circuit design in Fallstad. It's unrecognized and just shows a block because of how fast it is oscillating. If we adjust how long the charging and discharging time is by using a 10 microfarad capacitor instead of a nanofarad, we see the oscillating happening, and we can see that the buffers are acting as the power and ground sources as they flow through the resistor and capacitor, charging and discharging. Now let's get into how successive approximation works. Here we can see a block diagram of how successive approximation should work. An analog value, in this case coming from an AC sine wave, is held to a specific analog value and then sent through a comparator through the positive pin, with the negative pin working with a successive approximation register and a digital to analog converter, approximating what voltage is being outputted. Here we can see that block diagram expanded onto the schematic of our SAR ADC. For starters, we can see that this is the sample and hold, which is taking the analog input and it is ranging it into the 0 to 5 volts, which will hold a specific analog input. This is outputted to the positive pin of the op amp, while the negative pin is coming from this digital to analog converter. The way it works is from the clock, singular rising edges are being outputted. The first rising edge is sent to the first D flip-flop, which is preset with the value 1. What this means is that this AND gate will turn high, sending the digital analog converter to half of the reference voltage, which will set it to 2.5 volts, and that is compared with the digital to analog converter, and the output is then echoed back into the input of the D flip-flop, which then moves on to the very next output, which is sent another rising edge, and this process will continue until an approximated voltage is found.